If you asked me, out of all of my videos, which project was the most difficult, I would say that's easy, no question, without any doubt, hands down. The most difficult project is my homemade computer. I still think to myself, how could I have designed this when I did not learn electronics in school, I didn't have a nicely written tutorial to follow, I just randomly became obsessed with bringing my simple computer idea to life. I had to teach myself electronics and how they work, how to design and create my own circuit boards for the first time, and I failed a lot. There's literally blood, sweat, and tears in this project, and I'm not kidding. And by some miracle, I was able to make my computer read my own custom code language that I had to create so it can control lights, speakers, accept user input, draw on an Etch-a-Sketch, and many more. And I'll add a link to that video below, but today I really want to revisit this project and go into more detail about how it works. And I haven't looked at this in years. Luckily, everything still seems to be here. The 3D printed wood-stained filament still looks and feels great. I could have used simple push buttons, but that would have been easier, and I really like the feel of these old toggle switches. It's reminiscent of the very earliest computers. In the first video I show how I used all these accessories, but this video is more on how the computer works. And this looks like my original code that I wrote, with very simple programs. And that's exactly what I wanted, the simplest computer I can possibly create. So let's see how it works. Well, every computer ever made has one thing in common. It has to have a clock, a pulse, a heartbeat in a way. Most computers beat at very high speeds, like millions or billions of times a second. But let's build our own with simple components. It's time for my favorite part. We get to talk about the single greatest invention man has ever created, the transistor. The first transistor was created in 1947 at Bell Labs in New Jersey. All it does is block the flow of electricity unless a small amount of electricity flows through the center gate, which allows the main electricity to pass through. It's basically just a small switch. And yeah, that's it. But actually it's just what we need. There are no moving parts. It functions at near the speed of light. It can be manufactured in the trillions at microscopic levels. And most importantly, it can be arranged into building blocks that we call logic gates. That I made these a long time ago to help show how a transistor works. So this is the AND gate, so you need both buttons to be on. This is the OR gate, so either one can be on. This is my favorite, the NOT gate, which is on unless the button is pressed. Two NOT gates together can stay locked and actually remember the last state it's in. So in here I have 4 bits together, so I can write anything I want to these numbers and it will remember it as long as you maintain power, which is how the RAM chip works. So the data that we store will actually be used later to execute commands. Here, I'm using 2 NOT gates that are connected to each other. If one is turned on, instantly the other one is turned off. These 2 capacitors take a while to charge up, but when they do, they release electricity that turns one of the gates off, which instantly turns the other one on. But what if we just use one LED? We now have a very simple computer clock that will pulse about once every second, also called 1 Hz. For my computer, I decided to use the very famous 555 timer IC chip. But it's doing the exact same thing. It is pulsing and blinking as our computer's clock, a heartbeat for our computer, which will make sense in a little bit. So this is our speed for our computer. So the faster CPU clock speed, you can usually process more data. And I like using the 555 timer since I can use a variable resistor or potentiometer to adjust the speed. Next, we need a chip that will count upwards with every clock pulse. These 4 green lights are actually counting from 0 to 15. This is what it looks like when you count in binary, when you only have zeros and ones. I designed this 3D print to help show how simple the logic actually is. Each digit represents a value double the last, so from right to left, we have 1, 2, 4, 8, etc. And if the digit equals 1, flip it, and the next digit in order down the line. Comment below what you think this number would be. So we have a clock, we have a counter, and we need to store the program in memory. So this might help. This is the data sheet for our exact binary counter. And they even show you the transistor logic gates that are used to make up this chip. So the transistor flip-flops are connected in a way so with each clock pulse, it will export the correct number in binary in a similar way to the 3D print I created. But that data in the memory can also affect this chip and the binary counter. I'll show you what I mean. So let's first look at the data sheet for our RAM chip. And I like to visualize this RAM chip like a 16-story building with 8 rooms per floor. So if I want to read the data in this chip, I have pin 16 go low. I can read the green input numbers that will export our 8 bits of data. The first 4 digits are just data, which we call operands, but the next 4 digits are opcodes, and those actually control what the chips do. So these 4 lines actually feed directly into the chips themselves to control them. So if you're a visual learner like me, it might just help to actually write some code and show you what happens. We'll have the first 4 operands be low, and the next 4 opcodes be high, which is default, which means nothing special happens. So let's just store a bit or two in the first few addresses, but when we get to address 4, let's do something different. Let's drop that first opcode to 0, which is a direct line to the binary counter that will make it pause. So our program should essentially halt when it gets to address 4. So let's execute the program and watch that happen. As basic as this sounds, there are times in programming where you do want things to pause, halt, exit, so this is an actual function within real computers today. But the next program is a little more important. Just about every program you ever write is in some sort of loop, where it continuously goes through the main loop forever. Let's set that second opcode, which goes directly to the binary counter's reset pin. So when that pin on the binary counter goes low, it will reset the counter to go to 0, therefore creating an infinite loop. Of course, it doesn't have to be address 4, it could be 10, 12, it's just following our simple instructions that we put in our code. And it works, so we are caught in an infinite loop. And think about the potential of just this simple program. Those first 4 bits could control different notes and play music, maybe servos and turn robots. The potential is already here in this simple program. Another very important thing all computers do is jump within memory. Every time you are creating a function, that's what the computer is doing. It is jumping to that function in memory and then returning back to where it was. So this time, let's drop that third opcode to 0, which will trigger our read input of the binary counter. So our first 4 digits in RAM will actually be the new address that our binary counter will jump to. So we can make our binary counter count from 0 to 4 and then jump to another spot in memory, maybe address 8 in this case. And just for fun, on address 15, let's just turn all the bits on. And it's working, we're actually jumping in memory. Computers are always doing a lot of jumping. Maybe they're retrieving memory, or graphics, sound, user input, all within our forever main loop. And this computer is modular, so you can have any board added to the address line. For instance, we could have a chip that adds numbers. As simply complicated as this is, you can clearly see and follow what's going on. We have a clock pulse, we have a counter, we have memory, and that memory can execute code that can control the chips, data, user input, speakers, graphics, screens, but none of it would be possible without the transistor. So I hope you can tell that I have a real love for this computer, this project. It was a really difficult project. Hopefully now computers make a little more sense. I want to say it was fun hanging out with you, and I hope to see you again next time.